So in addition to graphing a parametric equation, we might actually want to take the resulting curve and write an equation for that in terms of x and y only. There's no exact method for doing this. If we can solve for t in terms of either x or y, then we could substitute this into the equation of the other variable to find an equation for our curve exclusively in terms of x and y. Here's an example. Suppose I have the following parametric equations describing my curve: x equals 2t plus 1 and y equals t minus 2, and the t is running from minus infinity to infinity. Since I can solve for t in terms of y, I have t equals y plus 2. I can take that value of t and plug it into the equation on the left above to get x equals 2 times y plus 2 plus 1, or x equals 2y plus 5. So whatever t is, then the point on my parametric curve must satisfy the equation that the x value is 2y plus 5. So all points on the parametric curve are on the line x equals 2y plus 5. And since t takes all values in the interval from minus infinity to infinity, and y equals t minus 2, y also takes all values from minus infinity to infinity, so the graph of the parametric equation is the entirety of this line. And here we see that as t runs from minus 6 to 10, the graph of this parametric equation coincides with the graph of the line. Here's another example, and again there's no sure and fast method of converting your parametric equations to an equation relating x and y, but sometimes you can recognize that some equation holds. And here, for example, if I have the parametric equations x equals 2 cosine t, y equals 3 sine t, describing a curve traced out when 0 is less than or equal to t, which is less than or equal to 4 pi. I know that cosine squared t plus sine squared t is 1. That's a well-known formula. And in the equations above, I see that x over 2 is cosine t, and y over 3 is sine t. So for any point on this curve, we must have x over 2 squared plus y over 3 squared equals 1. So in other words, the graph of the above parametric equation must coincide with at least part of this ellipse, x squared over 4 plus y squared over 9 equals 1. The curve traced out must be at least part of this ellipse, and if we check some points, if we check the point where t equals 0, we see that it's the point 2, 0 on the ellipse, and if we increase the value of t from 0 to 2 pi, we see we go around the ellipse exactly once in an anti-clockwise direction. And if we also graph the parametric equation between t equals 2 pi and t equals 4 pi, we see that we go around this ellipse a second time. So our parametric equation traces out this ellipse twice, moving in an anti-clockwise direction. Here we see that as t runs from 0 to 4 pi, the graph of the parametric equation x equals 2 times cosine t, y equals 3 times sine t, runs around this ellipse in an anti-clockwise direction, and by the time t gets to 2 pi, we've arrived back at the initial point, and then as we move from 2 pi to 4 pi, we trace out the ellipse once again.